we are starting work on determinant of a matrix. So before we see how to effectively compute it, we will first see a couple of remarks and properties that are super important and then that you will need to learn. So first observation is that the determinant is only for square matrices. So only a square matrix has a determinant. So if the matrix is not square, determinant is not defined. We cannot compute it. So any matrix 3 by 7, for instance, that is not square, doesn't have a determinant. Determinant is not defined. Only square matrix has a determinant. Also, every square matrix has a determinant, and it has only one determinant. Determinant of a square matrix is a real number. So it's a number. It's not a matrix, it is a number. It can be obviously negative, positive, or zero, and we need to be mindful of that. Also, several matrices could have the same determinant. That's okay. There's nothing wrong with that. So we will see, based on the properties, let's say all 3 by 3 matrices that are not invertible, they'll have the same determinant, which is 0. So that's fine. There's no problem there. Couple of properties that are important. First one regards the notation. So determinant of matrix A, we write that of A, so that's a number. It can be also written like this, so it's A, and then you have one bar on each side. You choose the notation. I prefer this one, that A. Important property, determinant of the matrix A is equal to determinant of its transpose. So that's something to remember. All these properties are very important and you need to learn them. So if I have two matrices, square matrices of the same size, n by n, then the product of the matrices AB is defined. And then the determinant of the product is product of determinants. So that's very important property. If my matrix A is invertible, then the determinant of the inverse is 1 over the determinant of the matrix. Very important property. For some matrices, it will be easy to compute the determinant. For instance, if my matrix is triangular, which means triangular upper or triangular lower or diagonal, in all those cases, the determinant of the matrix is simply the product of the entries on the main diagonal. Very simple to compute. But that's only for triangular matrices. For other matrices, it's much more complicated. We will see how it works. Another important property is if I have a row of zeros in a matrix or a column of zeros, then determinant of the matrix will be 0. So I don't need to do any computation. A matrix A is not invertible if and only if the determinant of the matrix is 0. And the matrix A is invertible if and only if the determinant is different from 0. So if the determinant is -6, matrix is invertible automatically. And then the last thing, if I have a square matrix, then the linear system AX equal B has unique solution if and only if the determinant of the matrix is different from 0. Which means for a square matrix, the system AX equal B has unique solution if and only if the matrix is invertible. So those are very important properties that we need to remember because they will simplify our life later on. The method to compute determinants, the one that we are going to use, is called cofactor expansion. So we'll see how that works. And one of the important things is that determinant A can be calculated by expanding using any row of a matrix or any column. It's our choice. The choice of a row is our choice. The choice of a column is our choice. We only need to pick one. No matter which one we pick, the result at the end will be exactly the same. This means it would be smart to pick a row or a column that has a lot of zeros in it. That will simplify our calculations. We do not have to do it, but it would be just smart to do it. So let's see how it works. For 1 by 1 matrix, it's simple. There's only one element, so the determinant is the element in the matrix. So we don't have many of these cases, so that one is just a remark. For any 2 by 2 matrix, and we said determinants are defined only for square matrices, for any 2 by 2 with 4 entries, A, 1, 1, 1, 2, 2, 1, 2, 2. So these indices here indicate the position in the matrix. So this is element in the first row, first column. This is element in first row, second column. This element is second row, first column. And the last element, A22, is in second row, second column. So these indices indicate the position in the matrix. So the determinant is just A11 times A22 minus A12 times A21. So that's it for square 2 by 2 matrices. Very simple to compute determinant. Couple of examples. I have a matrix here, A. So determinant will be negative 2 times 3 minus 1 times 4. So that's what I have here. Compute all this. Determinant is negative 10. So I know immediately that this matrix A is invertible because its determinant is different from 0. And notice matrix A is a matrix and determinant is just a number. So those are two different things. A determinant is a number and it is not equal to a matrix, obviously. So we don't want to make those mistakes. If we want to compute determinant of matrix B, again, it's going to be 2 times 2 minus 1 times 4. Oh, determinant here is 0, which means that matrix B is not invertible. C, oh, this is a diagonal matrix. So I can say immediately for a diagonal matrix, I know that determinant is product of diagonal terms. So it's 2 times 4. That's 8. This matrix is invertible. Or I can still apply the same rule as previously. That's just computation for nothing. Matrix D is 0, 2 by 2 matrix. So it has a row of zeros, so I know immediately determinant is 0. It has a column of zeros, so I know immediately determinant is 0. 0 matrix is not invertible, obviously. Identity matrix 2 by 2, I, is diagonal matrix. It has 1 on diagonal terms. So determinant is 1 times 1, which is 1. So identity matrix is obviously invertible. So if I have 3 by 3 matrix, there are two ways to compute. This spaghetti way, which I do not recommend. You can use it if you wish, but it's not really what I would like to recommend you because our cofactor expansion is more general approach. So what is cofactor expansion when I have a 3 by 3 matrix? How do I compute determinant? First thing, we know that we can pick any row or any column to expand. It's our choice. We can choose whichever one we like. So let's say we want to expand by row 1. So I always need to indicate by which row or by which column I am expanding. It's super important to indicate that. So here I say I will expand by row 1. So this is row 1 of my matrix. How it works. So determinant A, which is our number, it's equal to, and this is our cofactor expansion. And you will see negative 1 all over the place. So it's negative 1 to power 1 plus 1. You see the indices of the location of the entry. So this is the entry, A11, A11. So indices are 1 and 1. So my negative 1 to power 1 plus 1 times the entry So you have it here also. And then times determinant of a smaller matrix, 2 by 2. How do I get that smaller matrix? Well, entry is 1, 1. Therefore, I eliminate row 1 and column 1. So I'm left with a smaller matrix here with entries A22, A23, and the other row is A32, A33. So that's what I have here. So this is a number, determinant of this matrix is a number. So everything here is a number. So it's super important to indicate determinant A here, determinant in front. Okay, so that was the first term. Second term is again negative 1 times the entry is A12. So I need to eliminate row 1 and column 2 from my original matrix. What I'm left with is entries A21, A23, and A31, A33. So again, it's negative 1 to power 1 plus 2 times A12 times determinant of a smaller matrix. And then the last part is again negative 1 to the power summation of coordinates, which is 1 and 3, times A3, and then times determinant of a smaller matrix that I get by eliminating row 1 and column 3. So everything here, when I finish computation, here I have a matrix 2 by 2, determinant of 2 by 2. We know how to compute it is, in this case, A21 times A32 minus A22 times A31. So I need to compute 3 determinants of 2 by 2 matrices. Now we want to notice something. We have a term here, A11, A12, A13, that multiplies other pieces. So imagine, for instance, that A11 is 0. While I will have negative 1 to power 1 plus 1 times 0 times determinant of this matrix. And I would need to compute this part. Well, whatever the result is, I'm going to multiply it by 0. So if A11 is 0, well, all this is 0. So there's no point of computing this. So now you understand, if I choose a row or a column that has a couple of zeros in it, well, there's a bunch of pieces that I do not need to compute. That's the advantage of choosing a row with a lot of zeros. If A11 is 0, this part I don't need to compute it. And at some point I will not need to even write it down. I only have these two pieces to work on. So there is advantage of choosing a row or a column with a lot of zeros, whenever possible. Same matrix. Now let's say somebody wanted to expand by row 3 instead of row 1. You don't have to, but let's say just for the sake of the argument that we want to see how that works. By the way, the result will be exactly the same. You'll get the same determinant of your matrix, no matter the row you choose or no matter the column you choose. So you pick one that you like. So let's say somebody, instead of picking row 1, said, oh, I like row 3 and I'm going to expand by row 3. No problem at all. So I have row 3 here. So I have my entry A31. So I start negative 1 to power 3 plus 1 times A31 times the determinant of a smaller matrix. How do I get a smaller matrix? Well, I'll eliminate row 3, column 1. And I get a smaller matrix here. So I need to compute the determinant of that. So that's the first part. Plus negative 1 to power, coordinates are 3, 2, so to power 3 plus 2 times entry, the value, numerical value of the entry 2, A32, times determinant of a smaller matrix that I get by eliminating row 3 and column 2. So I have A11, A13 on the top, and A21, A23 is the second row. Last part, I have to work with A33, so it's negative 1 to power 3 plus 3 times A33 times the determinant of a smaller matrix that I get by eliminating row 3 and column 3. So this is the smaller matrix. Okay, fine. So I do the process. The end result will be the same as previously. Imagine somebody wants to expand by column 2 instead of using rows. Somebody is in love with columns. For some reason, there is some advantage to expand by column 2. No problem at all, result will be the same. The procedure is the same. So this is a column 2. So we start with the entry A12. So I have -1 to power 1 plus 2 times A12 times the determinant of a matrix that I get by eliminating column 2 and row 1. So I have A12, A23, it's A21, A23, and then the second row A31, A33. Nice, it's here. Second part, -1 to power, so the entry is A22, so 2 plus 2 times A22 times determinant of a matrix that I get by eliminating column 2 and row 2. So these indices 2 and 2 tell you which row and which column you need to eliminate. So I have A11, A13, A31, A33. Here it is. Plus -1, the last piece is entry at the position 3, 2. So it's -1 to power 3 plus 2 times A32 times the determinant of a matrix that I get by eliminating row 3 and column 2. Okay, so I have A11, A13, A21, A23. Here it is. Now I will need to compute all of these determinants separately and then bring everything together. And the result will be exactly the same as if I expand by any row or any other column. Again, if one of these entries is 0, then this part I don't even need to compute it because I will multiply by 0. So that's the advantage of actually choosing a row that has a lot of zeros or a column that has a lot of zeros. There are pieces of computation that you don't need to do. You see I have 3 by 3 matrix, and to compute the determinant of the 3 by 3 matrix, I end up having to compute 3 determinants of 2 by 2 matrix. So imagine if I have a 4 by 4 matrix, I will need to compute determinant by actually computing 4 determinants of different 3 by 3 matrices. For each of the 4 3 by 3 matrices, I will need to compute 3 determinants of 2 by 2 matrices. So suddenly you see the complexity in this process. Again, there is an advantage of choosing row with a lot of zeros or a column with a lot of zeros. It simplifies the computation. Some simple examples where it's easy to compute determinant of a 3 by 3. If I have a 0 matrix, well, it has a row of zeros or a column of zeros, so obviously determinant is 0. Identity matrix is a diagonal matrix, so determinant is product of diagonal terms. It's 1 times 1 times 1, so determinant is 1. Identity matrix is invertible. If I have negative identity, well, again, it's diagonal matrix, so the determinant of a diagonal matrix is product of diagonal terms. So -1 times -1 times -1. Result is -1. So minus identity is also invertible. Last example, matrix B. Here we see that we have a row of zeros. We are going to take advantage of this. So we need to say, okay, I'm going to expand by row 2. Very important to say by which row you're expanding. I'm expanding by row 2, and this row is full of zeros, therefore determinant of B is 0. So no need to compute anything, I just need to indicate this. Expand by row 2, row of zeros, determinant B equals 0, goodbye. Work done. Now if somebody wants to expand by row 1, that person is welcome to do it. At the end of the day, determinant will still be the 0. But that person is going to work a lot more than somebody who knows what he's doing. So it's very important to learn the properties. When you know the properties, you simplify your life. You go faster in computation. Here are some examples of different matrices where I can take advantage of my knowledge. So if I have a diagonal matrix, like this one here, I know already that determinant of a diagonal matrix is product of diagonal terms. So determinant of this matrix is 3 times -4 times 2 times -5. Use your calculator, compute, and that's it. So the answer is 120. So the determinant of this matrix is 120. This matrix is invertible. Beautiful. We know that. So let's say this matrix here, 3 by 3. I can see several things. I have a row of zeros, so determinant is 0 immediately. I have a column of zeros, so determinant is 0 immediately. Or I can say, hey, but this is a diagonal matrix, and diagonal entries are 9, 0, and -2. And I know that determinant of a diagonal matrix is product of diagonal terms, which is 9 times 0 times -2, which is 0. So whichever way you turn it, determinant is 0. What do you choose? Whatever you see first. Your choice. Just need to specify it. Here I have a 0 matrix 3 by 3, so obviously determinant is 0. Here, determinant of this 2 by 2 matrix, I have a row of zeros, therefore it's 0. Or you can say, oh, I have a column of zeros, so determinant is 0. Or you can say, hey, this is a diagonal matrix, and diagonal terms are 0 and 1, and product of diagonal terms is actually determinant. So 0 times 1 is 0, so determinant of this matrix is 0. Here, I have again a diagonal matrix, so determinant is 2 times -1 times pi. So -2 pi. Determinant of this matrix is -2 pi. Matrix is invertible, everybody's happy. What about this matrix here? Well, this is upper triangular. Great. I know that determinant of upper triangular matrix is very simple to compute. It's product of diagonal terms. So determinant of this matrix is 3 times 1 times -2. So determinant is -6. Simple, simple. This matrix here is a triangular lower. Again, a determinant of a lower triangular matrix is product of diagonal terms. So determinant is 4 times -3 times 1, which is -12. So determinant of this matrix, which is lower triangular, is -12. Similarly, for this matrix, 4 by 4, determinant is product of diagonal terms because this is triangular matrix. So all I need to say, triangular matrix, determinant is equal to product of diagonal terms, which is 3 times 1 times 4 times -5. Work finished. So in the cases that we are going to meet most of the time, we will have matrices where we really need to compute the determinant. It's not going to be so obvious from just looking at the matrix. So in that case, we use cofactor expansion. Here is an example, and the question is going to be worded very simply. It's find the determinant of A, or compute determinant of A. Very simple. So here I have a matrix, 3 by 3, and there's no zeros. So I cannot take advantage of any row or column containing 0, unfortunately. So I can pick any row or any column I like to compute the determinant. For the pleasure, I picked row 3 for no good reason, just like that. I felt like row 3 is ugly enough, so I can work with it. I always need to indicate which row or which column I use to expand. It's mandatory. You don't do it, you pay for it. You need to indicate clearly which row or which column you use. It's very important. Otherwise, we don't know what you're doing. So here I indicate expand by row 3. Okay. So a computation of determinant by expansion by row 3. Here I put my matrix, so we see it, and let's go with the procedure. So what do? We expand by row 3, so this is row 3. First entry is 7, and its location is row 3, column 1. So I will have -1 to power 3 plus 1 times 7 times the determinant of a smaller matrix that I get by eliminating row 3 and column 1. So what I have left is matrix which is 2 by 2, 2, 3, 5, 6. So that's the first piece. Plus, second piece, the entry 2, 3. So I have negative 1 to power 2 plus 3 times the entry, which is 8, and then times the determinant of a smaller matrix, 2 by 2, which I get by eliminating row 3 and column 2. So what is left is 1, 3, and second row is 4, 6. That's what I have here. Plus, the last entry is 9, and its location is 3, 3. So I have negative 1 to power 3 plus 3 times 9 times the determinant of a smaller matrix that I get by eliminating row 3 and column 3. So 1, 2, 4, 5. Here it is. Now, I need to compute every single one of these determinants of 2 by 2 matrix. Fortunately, that's not complicated. So we start here. Negative 1 to power 4 is 1, times 7 is 7, times the determinant of this 2 by 2 matrix. So it's 2 times 6 minus 3 times 5, which is 15. So 12 minus 15, that's what we have here. Plus, negative 1 to power 5 is negative 1 times 8 is negative 8 times the determinant of this matrix. So 1 times 6 minus 3 times 4. So 6 minus 12. That's what we have. Plus, negative 1 to power 3 plus 3. So negative 1 to power 6, which is 1, times 9 times the determinant of this matrix. So 1 times 5 minus 2 times 4. So now we compute all this, and it turns out that the determinant is 0, which means that the determinant of this matrix is 0, which means the matrix is not invertible. Now, there's no way for you to just figure out from these numbers here what is the determinant. It's not simple, it's not obvious. So we need to go through the process. Now, we would get the exact same solution, the exact same result, if we choose, let's say, column 3 or column 2 or column 1 or row 2 or row 1. It's our choice. Whatever we choose, we will get the same result. We just need to choose one, do the work, and it's finished. We don't need to do it 7 times, just one. You pick one, the one you like, and you go for it. So what happens if I have a 4 by 4 matrix? Well, the procedure is the same. I use my cofactor expansion to do the work. Here, I alternate the notation because we said determinant A is most of the time written like this, but sometimes you will have your matrix and then you'll have these single bars on each side. So this means determinant of a matrix inside. So determinant of A is a number, and this is just another notation for it. You can use that A or this notation. It's up to you, but be careful. You see that these are just simple lines on each side. So again, we can pick any row we like or any color we like, and we will get the same result. Now, what would be a smart choice? Through our procedure, we saw that we are multiplying by those numbers that are on the row we picked or in the column we picked. So it would be smart to pick a row or a column with a lot of zeros, because 0 times any other number is 0, so we don't even need to compute. So in this case, a smart choice would be a row 3 or column 2, because both of them have 2 zeros. Obviously, you can pick row 1, there's nothing wrong with it. You're just going to compute for half an hour. And you'll get the same result as somebody who was smart and picked row 3 or column 2. So it's your choice what you pick. You can pick last row also, it has 1 0, but the smartest choice would be either row 3 because it has 2 zeros, or another smart choice would be column 2 because again it has 2 zeros. Whichever one you pick, it's going to be fine. You will get the same result. Just be smart. So in our case, for the purpose of the example, we chose a column 2. So this column here, because it has 2 zeros, that was a smart choice. So again, we use our procedure, cofactor expansion. So determinant A is equal to, so I have my column 2 that I'm using. So the entry here is 2, and the entry is in a position row 1, column 2, so 1, 2. So I have negative 1 to power 1 plus 2 times the entry at the position 1, 2, which is 2, times the determinant of a smaller matrix that I get by eliminating column 2 and row 1. So entry 1, 2, I eliminate row 1, column 2. So what I'm left with are these numbers. So smaller matrix 3 by 3, first row negative 4, 1 and 3, here it is. Second row 3, 0, minus 3, here it is. Third row 2, negative 2, 3, here it is. And notice again I use a new notation with 1 bar on each side. It saves me some space. I could still use that of A, but it's fine. I use this. Fine. So that's the first piece. Second piece in the column is entry 2, 2. And the value is 3. So I have negative 1 to power 2 plus 2 times the entry 2, 2, which is 3, times the determinant of a smaller matrix that I get by eliminating row 2 and column 2. So I get a smaller matrix 3 by 3, and the first row is 1, negative 3, 4, here it is. Second row is 3, 0, minus 3, here we go. And the last row is 2, negative 2, 3, here we go. So the determinant of A is equal to these two pieces here. I need to do the computation. So negative 1 to power 3 is negative 1, times 2 is negative 2. So I copy the part from above. So this is 1 times 3 is 3, and I copy again a part above. So you see I only have now to compute 2 other determinants of 3 by 3. If I chose row 1, I will have 4 of them. That's not smart. And the result is exactly the same. So be smart. Pick a row with a lot of columns, a lot of zeros, or a column with a lot of zeros. Be smart. Now, another thing of being smart is to be clean also. So I need to compute, in order to get determinant A, I need to compute determinant of this 3 by 3 matrix and determinant of this 3 by 3 matrix. So I need to evaluate these two determinants. I don't want a mess. I want it clean and clear. So I'm going to compute determinant for each of those matrices separately. I'm going to be smart. I want everything to be clear and clean so everybody can see it and check it, and I can double check my work. So to compute determinant of the first 3 by 3 matrix, again matrix is here, I can pick any row or any column I like. Now I see a 0 in the middle here. So I could pick a row 2 or a column 2, that would be a smart choice. There's nothing wrong with picking row 1 or row 3 or column 1 or column 3. There's nothing wrong. It's just dumb. I need to work too much for nothing. The result will be the same. So be smart. Pick a row with a 0 or a column with a 0. So here, for fun, I pick a column 2. So I'm going to expand by column 2, and I must specify this. If I don't, that's no good. I lose points. Because this is part of the procedure. I need to specify a row or a column by which I expand. Be careful. So the procedure is the same. So I picked column 2. So I have my entry with coordinates 1, 2. So it's negative 1 to power 1 plus 2 times the entry 1 times the determinant of a matrix that I get by eliminating row 1 and column 2. So the matrix is 3, negative 3, 2, 3. Here we go. Then 0, but 0 I don't care, so I don't need to write anything. And then the last piece is related to the entry in the row 3 and column 2. So negative 1 to power 3 plus 2 times the entry, which is negative 2, times the matrix that I get by eliminating row 3 and column 2. The entries of the matrix are -4, 3, 3, -3. Here it is. So now I only have two pieces. So -1 to power 3, -1, times 1 is 1. So -1 times determinant of this 2 by 2 matrix is 3 times 3 minus 3 times 2, so it's 9 minus 6, so it's 9 plus 6. Be careful with the signs. Plus, here I have -1 to power 5, which is -1, times -2, so that's 2, so plus 2 here, times determinant of this smaller matrix, which is -4 times -3, which is 12, minus 3 times 3, which is 9. Here we go. Compute everything. Determinant of this 3 by 3 matrix is -9. The result is exactly the same if I chose row 2, or row 3, or row 1, or column 1, or column 3. Whichever one I choose, the result will be the same. Determinant is -9. Okay. Let's compute determinant for the other matrix. Here again, I have a 0 in the middle. That's beautiful. So this time, just to vary a little bit, I'm going to expand by row 2. So I must specify this. So I'm expanding by row 2. Okay. So in row 2, I have entries 3 and -3. Fine. So this entry here is located in row 2, column 1. So it's -1, 2 plus 1 times the entry times a smaller matrix 2 by 2 that I get by eliminating row 2 and column 1. So what I have is a matrix -3, 4 and -2, 3. Up here. Next, I have this entry at the position row 2, column 3. So position 2, 3. So it's -1 to power 2 plus 3 times the entry, which is -3, times determinant of a matrix that I get by eliminating row 2 and column 3. So the matrix is 1, -3, 2, -2. Now, I need to compute determinants here. So -1 to power 3, -1 times 3, -3 times -9 minus 8, so -9 plus 8. Here -1 times -3 is 3, so here is product 1 times -2, -2, minus 6, so it's plus 6, so -2 plus 6. Do the computations, complete everything, determinant of this matrix is 15. So that's how I did it, piece by piece. Now I bring everything back together. Combine the pieces, because my goal was to compute determinant of A. So determinant of A was -2 times determinant of this matrix and plus 3 times determinant of this matrix here. So determinant of the first part was -9, determinant of the other part was 15, so I combine everything now. It's going to be -2 times -9 plus 3 times 15. Compute, I get 63. So determinant of matrix A is 63. By the way, this is matrix A, 4 by 4. This matrix here is 3 by 3. So this is not a matrix A. So do not give it the same name as the name of your original matrix, because it's not the same. So if you wish to give a name here for this matrix, you can call it B. This, call it C. But don't call two different matrices with the same name. That doesn't work. You will be penalized for that. So that's how we compute the determinant of 4 by 4 when we have a choice of rows or columns that have a couple of zeros in them. So we need to be smart and choose those rows or those columns. Otherwise, we work for nothing, and the end result will be exactly the same, but we will take too much time to compute it. Finally, a couple of useful properties. If I have A matrix, n by n, so square matrix, then a linear system, Ax equal b, has a unique solution if and only if determinant of a matrix A is different from 0. So that means when I have a square matrix, so square system, Ax equal b, that system will have unique solution if and only if matrix A is invertible. So that's equivalent. So those equivalent statements need to be learned. They are very useful, and we can jump from one result to another very quickly. So we need to learn them. Important remark, when I have a square matrix, n by n, and if the determinant of that matrix is 0, which means matrix is not invertible, then the system Ax equal b either does not have a unique solution, so that's for sure. It cannot have a unique solution. What are the options? So remember, any system Ax equal b has either no solution, or exactly one, or infinitely many. So what we learn here, when our system is square and determinant is equal to 0, which means matrix is not invertible, we learn that Ax equal b cannot have a unique solution. So we are left with two options, either no solution, in which case that means that there is a contradiction in the system, so the system is inconsistent, or another option is the system is consistent, and in that case it has infinitely many solutions. Unfortunately, we cannot tell what's the situation. We need to go and try to solve the system, and then we will see. So we learned that when your matrix is invertible, then your system has unique solution, but when your square matrix is not invertible, determinant 0, then the only thing you know is that that system does not have a unique solution. Maybe it has no solution at all because there's a contradiction in the system, or the system has infinitely many solutions because there's no contradiction, system is consistent. And we do not know which one of those cases we are in. We need to try to solve. Last part, if I have a homogeneous system with a square matrix, so A square, and homogeneous system is Ax equals 0, well, that homogeneous system has infinitely many solutions if and only if determinant of a matrix is 0, which means the system has infinitely many solutions if and only if matrix is not invertible. Determinant 0 means matrix not invertible. By the same token, we know when determinant is different from 0, so let's say determinant is 5. That means my matrix is invertible, which means Ax equals 0 has a unique solution, and that solution is x equals 0, because we are dealing with homogeneous system here. So these are things that we need to learn. Very important things, very important properties. We need to learn them and be able to jump from one to another. And the last property we need to see is the one that says that determinant of a product is actually product of determinants. We remember that product A times B is not equal to B times A. We cannot change the order of multiplication of matrices. We know that. But for the determinant of A times B is the same as determinant of B times A, because determinant of the product is product of determinants. So determinant of A times B is determinant of A times determinant of B. Here you have an example, two matrices. You have product AB and BA, so there are two different matrices. Compute determinant for each, you will end up with minus 12 in each case. This is just an illustration. So the result that we need to remember is the determinant of the product is product of determinants.